So today's presentation is on Python parallelization using Ray code. My name is Dean Wetherby. I've been doing machine learning engineering for a couple of decades now. My specialty is in computer vision, which is image and video analysis, stuff like face recognition, optical character recognition, object detection and tracking. That's kind of my specialty. So I discovered Ray really early on. Ray came out of Berkeley's RISE lab, and I just happened to need some distributed processing for a data ingestion pipeline that I was working on. And although I started prototyping it using Celery, which is another distributed framework, I quickly switched over to Ray, and I just found that it worked better with my brain. And so I found over the last maybe 6 or 7 years different places where I can use Ray to great effect. One of them was at the DARPA Machine Common Sense project, where I was the tech lead for an evaluation team. So we had to run thousands of Unity scenes and use an AI agent to determine whether or not they thought the scene made sense from a common sense perspective. And the first time we ran this evaluation, it took 6 weeks for us to get it done, because we were doing it like with love, right? Creating an EC2 instance, AWS EC2 instance, running scenes and doing everything very manually. And when I took over as the tech lead, that was the first thing I tackled. And I did that with Ray. So we went from a 6-week evaluation process down to 5 days using Ray. So we were able to spin up hundreds of GPU instances and run thousands of scenes, simultaneously for 3 performers. And most recently, created a AI inference engine using Ray Serve. We're not going to get into that today, but I have found places to use Ray throughout my career so far. So Ray has a lot of offerings. Ray Data, Ray Train. So if you do model training, Ray can do this in a distributed fashion that may interest you. Ray Tune is for hyperparameter tuning if you want to explore what settings create the best model for yourself. I had already mentioned Ray Serve, and of course there's a reinforcement library which I've done nothing with. But Ray Core is the foundation for all of these other Ray libraries, and so that's what we're going to be focusing on today. Ray is actually like platform agnostic. So what I found really nice about Ray is you can prototype code on your laptop, then you can move it to an on-prem server and run it there, or you can build a giant like AWS EC2 cluster and run it there as well. There's no changes in the Ray code, it's just your configuration. And so that is a really nice way, as someone who likes to take research code and get it productionized, Ray is a beautiful way for me to make sure it works on my laptop on four processors or something, and then just deploy it to a 1,000-node cluster and run it on all the data. So that's kind of our motivation here. I should also mention that Ray is deep learning framework agnostic too. So if you are really good with PyTorch, for example, but then you find a TensorFlow model, like if you can write it in Python, Ray can run it. So, so I find the versatility there really, really good. So I have a couple links here. Ray.io, that's the main, their main website. We also have Ray Docs. A large part of this Jupyter notebook is driven by examples that are in the Ray Docs, except that I'm going to walk you through them instead of you having to figure them out yourself. And then I should mention too that another link here is Anyscale. Anyscale is the managed platform for Ray. So if you're at a small company or you have a startup or something and you don't have like DevOps or MLOps people to manage a Ray cluster for you, you might be willing to talk to Anyscale about their managed platform solution. So let me close these links. Okay. Let me clear out the cells here. Okay. So like like any of these things, pip install whatever that package is will work, right? Pip install Ray will work, but you will not get a dashboard. And that's something I want to show you so we can explore some of the tabs in the dashboard. To get Ray core with the dashboard, you're going to install the default option for the Ray package. I already have this installed, but we'll run it anyway. Later, if you are so interested, you can install Ray data or Ray training or Ray serve just by providing those options into the pip install command. Okay, so we have Ray installed in our environment. Let's start up a cluster. And it's as simple as importing Ray and running Ray init. So we'll give that a second, and then we'll run over to the dashboard and look at a couple things. Okay, so Ray's running. We'll go over to the dashboard. There's a couple tabs here. We're not going to look at Ray jobs or Ray serve. Remember, we're just trying to do the Ray core to explain the foundations of Ray. But we can go to the cluster. And if I collapse this, excuse me. So this is my host, the desktop. It's just named desktop. And if I expand it, we can see that my Jupyter Notebook is running here. And then if I scroll down, we just see a whole bunch of Ray idle workers. Okay, they're just sitting there waiting to do something. If I open my Windows Task Manager and I look at the Performance tab, you'll see that this machine has an 8-core processor with hyperthreading, so effectively I have 16 cores. Ray, by default, if you don't provide any arguments to init, will create a Ray worker per CPU that you have. So basically I have 16 workers here if I just run Ray init. Now, as a developer, I have Chrome running. I got to check email. Actually, on this top, I'm running OBS to do a screen share, screen recording. Right? I don't want Ray to hog all of the resources. So it'd be better if I brought down the server, and that's easily done by running Ray shutdown. So that the cluster came down. And now what I want to do is I want to restart the cluster, but I want to limit the number of CPUs, number of worker nodes that it's using. And Ray will manage GPUs as well. And this has a 3060, but we're not doing anything intensive with GPUs, so I'm just going to tell it, when you spin up the cluster, don't manage any of my GPU resources.
Dean, can I ask, so
yeah.
Is Ray in it like is that a blocking call, or is it like a signal to something that starts a process somewhere else? I'm trying to understand how you're like continuing to work through the notebook, and maybe that's telling the story in itself.
Yeah. Yeah, I'm not sure how to answer your question.
Okay.
Yeah, it's a good question though. So I'm just waiting for the new cluster to init. Here we go. And so now we see my Jupyter Notebook, and now we only have 4 workers. So now I feel a little more comfortable about the screen recording and everything else that's going on. We're not doing anything super intensive, so I think 4 workers will be fine. Okay. So if we look back over at the dashboard and scroll over a little bit, you see this object store memory that's using 0 bytes out of nearly 2 gigs. So this object store is really the secret sauce on what Ray is doing. Is all the data and execution all happens through that object store memory. And so we're gonna go very low level with the object store just so we have a good understanding of that and work our way up to some other fundamentals. I should mention, throughout this Jupyter Notebook, I have hyperlinks. I tried to be pretty thorough with this, but wherever I'm talking about a particular topic, there's a hyperlink that takes you straight to the Ray docs for that particular thing. Okay. But by the way, I didn't say this ahead of time, but I appreciate you, Matt, jumping in and asking a question. Feel free to interrupt me at any point. So we have this Hitchhiker Guide to the Galaxy variable here. Answer to everything is 42. And what we want to do is, you don't really do this as a Ray developer, but just to explain the object store, we're going to try to put that value into the object store where we can do some things with it. And the way you do that is through array put. And then it returns something that I'm calling an object reference. And so we'll just print out the object reference. If you're new to Python, fall in love with F strings. And I particularly love the equal sign on the F string, which prints the variable name equal and then whatever the value is. I tend to do that a lot. So we move this value 42 up into our object store. And what we displayed here is the object ref is an object reference with this whatever memory address or something like that. Now, for me, my mental model of the object store is these things are pointers. So I think about this object ref as a pointer to the value 42. My background is C++. If you're like a TypeScript person, maybe that's a future or something. Maybe that's a better mental model, but come up with whatever mental model you need to kind of wrap your head around this. If we go over to the dashboard and refresh, it doesn't always stay up to date. We can see that the object store is not 0 anymore because we moved that 42 up there. Big shocker, right? And then so we can also retrieve this value in the object store using array get. And you call that on that object reference, pointer or future or however you want to think about it, and then we can print the answer. And it's obviously 42. So now we're able to move things up to the object store and pull them back. Integers, floats, strings, all those kinds of things are easy to move up there. And then I have this last cell here. I'm using my favorite test library, Faker. I use this for unit testing or when I just need to create some kind of fake data. Because I don't want to foobar baz everything. So I'm using Faker to create a fake Python dictionary, move the dictionary up to the store, and we're going to print out the value of the dictionary and its reference. The fake PyDictionary is completely random, so we have to run this to see what it put up in there. So we can see that Faker made these key values in the dictionary with decimals, integers, strings. Sometimes it does date time. And then you can see the object reference here of that value. We can run it again and get a different random. Here we got a URL, a date time, right? So all that stuff is easy to move up to the object store. So it turns out anything that you can pickle, you can move up into the object store. That's really how this works. I have a note here just to remind myself that these remote objects are immutable. So that means once you move them up there, you can't change them. You can't increment a value or whatever. You have to make a new object in the store. This is because all the worker nodes are using that store to coordinate their work, and so they can't change values under it. It's like a safety thing.
Is there like kind of a network transparency? Right now you're working on a desktop, what single machine?
Yeah.
You talk about moving to a cluster. In a cluster setup, you're gonna have multiple nodes, presumably.
That's right.
And does the object store just get dropped on one of those nodes, or are they a separate node or something? And then
you can use an external Redis if you want to set that up, and there ends up being an object store. So if you start up 10 EC2 instances, for example, there's going to be an object store on each of those instances.
Okay.
All right. So you can externalize it using Redis. So if you need a really big object memory store, that would probably be the best thing for you to do.
Okay.
Yep.
Cool.
Yep. Okay, any other questions before we move on? Object store is pretty simple. Put, get, right? Put, get. All right. If you can pickle it, you can D or unpickle it. get it back. Okay, so all right, cool. So we can move data up into the object store. Well, how do we execute code in these Ray workers? So Ray has this thing called Ray task, and a Ray task is simply a Python function that's decorated with @ray.remote. And so we have a Python function here that doubles, that just takes in an integer, returns an integer, and we just like x plus x it. That's a regular Python function, and we decorate it with @ray_remote. And what that does, well, let's run this code, and I'm just going to print out the double, which is the function, and we'll see what it says. Right, so we created a double, and what it is a ray_remote function that's stored at some memory address. So I think of this too like a function pointer. You can maybe come up with your own scheme there, but so now this task is actually up on in the object store, and like these other objects that got pickled, actually this function got pickled. That's how this works. This function got pickled, it moved up into the object store. So when a worker gets through the scheduler a job to run a task on a piece of data, it's going to go to the memory address 0x7f whatever, pull this function down, unpickle it, and now it has the function to execute. Right? So it's really, I think it's really slick how Ray does that.
Quick question.
Yeah.
Or maybe a very robust question that you should not answer right now. How do you handle, like, or I guess, does it literally use pickle, or does it do something like pickle? Because I'm wondering how you pickle a function which might have, like, external scopes.
Yeah. So no, that's a great question. We're not going to get into that, but
okay,
but I'm going to tell you. But I'm going to tell you there's some gotchas with using Ray, and sometimes the way you've been developing Python code outside of Ray doesn't fit with the Ray model. Okay. So like if you open a socket or something, or a database connection or something like that, that's not pickleable. So you end up doing things like, I would have opened this one time and then reused it a whole bunch of times, but you don't know what worker is running that piece of code, so you actually have to reopen the database connection every time.
Well, that's a great point. Okay.
Yeah, so I didn't want to get into that, but I'm glad you asked it, because
that's a very good practicality attached to the very philosophical question. That's great. Thank you.
Yeah. Okay. But I addressed your question though.
Yes.
Okay.
Closures are probably a no-go.
No. There's some limitations, but you're gaining so much in the parallelism that you have to let go of some of that inefficiency. Is what I've found.
So you're doing everything in a notebook here.
Yeah.
In the context of a bigger project where you start up a cluster somewhere, how do you go about like importing so that any of these remote functions that you have are discovered and registered? It seems like all the registration happens just by that. Is it just a matter of just doing an import, like in your cluster initialization? You import all of your...
There are a couple ways to do this. I actually was tempted to do like a Ray job. Ray has a CLI. I'm not showing the CLI in the Jupyter notebook, but there's a way you can start up a cluster with CLI commands, and then you can actually have a big cluster, and then you could submit Ray jobs, and you can provide it a Python file to execute as part of that job, and like the Ray job submission copies it up, and then they all execute it. So there's a couple of different ways for you to do that. Ray is super flexible, and you can use it in a lot of different ways. So I don't find that I use the CLI very often, but you do have that option.
Like an Airflow alternative?
A lot of people compare this to Spark or some other things, but I'm not familiar with either of those. Actually, I have a Ray hammer, and I walk around hitting things with my Ray hammer.
Cool.
Yeah. Okay.
I guess I'm going to ask a question. What do you do about dependencies that you might need?
Yeah, I actually that's at the very end. That's like my big hurrah moment. Okay. Cool. Yeah, but thanks. Okay, so we have this Ray task, which is a Python function just decorated with ray_remote. And the way you invocate this Python function is, since it's a remote function, you just call the thing .remote, and then all your function arguments go inside of the remote rather than associated with a double. And the execution of this task returns a reference, just like the ray put. And so we'll run this. So basically we're going to double the answer to everything, which was 42, right? And then I'll print out the reference itself, and then we'll do a ray get on that reference, and we'll compare. Okay. So as you can see, when I call this ray task, it returns an object reference. And then you have to ray get it to get the actual value. So 42 doubled is 84. Does that make sense? The reference stuff? Okay. And what's really cool, and this is what Ray is doing internally, is you can also pass a result a reference itself to your function rather than the value itself. So we have this result reference, which was the act of doubling 42, so it's 84. But really what we're passing in is this into our doubler, and then we'll get another answer, and we can do a ray get on that. And so it's the double of the answer to everything, which is 168, and it's an object reference. So ray task can run on values or on object references themselves.
In that example, if you had the wrong type in there, is it going to blow up in a nice way so you help you diagnose it, or is it just assume you're going to figure out you're smart enough to pass in the right object reference or something like that?
There's a lot of exception handling in Ray, and so there's like Ray actor errors, Ray other errors. I don't know if I should actually just pass in. We could do that. That's why I love Jupyter. I actually don't love Jupyter Notebooks, but that's why it's useful. So what do you want to do? Like just pass in like a string, Bob, which we wouldn't expect anything to happen, or what?
Well, that one is probably going to return Bob. The funny side is that.
Oh yeah, it might double Bob.
It'll be Bob probably, but
we could do that. That's true.
But I guess that's more of a commentary on Python.
Yeah, it is Bob. It is Bob. Yeah. Yeah, I'm not sure what.
So it's not paying any attention to like type annotation.
I mean
in a
that's.
particular way.
I mean that's kind of on me, right? My
Yeah.
my function, I should assert that it's an int or whatever. But if it runs it like a divide by zero or something that really throws an exception, Ray wraps internal exceptions into a Ray exception, which you have to kind of dive into if you capture that. So I'm not sure how really to execute that at the moment. And then, of course, Ray task can call other Ray tasks. So right from the Ray docs here, I have a Ray task that just returns a value of 1. And then I have another Ray task that calls that task basically 4 times. Okay? And remember, the return of a task is an object reference. So when F returns this 1, it's really returning an object reference or a pointer to that value of 1. So G gets a list of object references, and G returns an object reference that points to the list of object references. Hopefully I'm not losing you. So when we run ray.get, we print out ray.get on G remote, we're dereferencing basically that first object reference, and we should get a list of object references that in turn those point to 1. So when you nest, you have to kind of be careful about where you're getting or what you're doing with the object reference stuff. If we change this, to do another ray get, so remember ray get on G remote returns a list of object references. If we do another ray get and execute it, now we're getting our list of 1s, right? But this like ray get G remote is like a little much. So another way you could do it, and I'm just pointing out like a couple gotchas if you decide to look into this. Another way to do it is we'll do the same thing as G, but we'll just call it H. And we're going to do in a list comprehension call f 4 times. So remember, this would return a list of 4 object references, and we do array get inside this function. So now when h returns, it's an object reference to a list of ones, right? As opposed to the way we were doing it with g. So I'll execute this cell, and we'll just see, that h remote should be an object reference, and array get should be the same as our array get g remote, because we just moved the array get inside, right? Okay. Hopefully that makes sense. If you do anything like semi-complex with array, you will start doing remote functions, and that you just need to be aware of what's happening, because you end up with lots of array gets to finally get down to your value. Okay.
So the object references seem to be tied to a particular execution. Like I was observing higher, you were having your function return 1 each time.
Mm-hmm.
In some universe, maybe the system would, the object store would be like, hey, that's a duplicate, I already have an object like that. But I saw that the identifiers, they all seem to be different. So they're tied more to execution rather than a content in the object.
Right. Yeah, that's a good point. Yep. Any other questions before we move on?
Is there a mechanism for clearing out that global store, or how long does that run for the?
Yeah. So I guess you could talk about there's spillage too. So if you do run out of space, it'll start writing to disk, and then Ray, when things go out of scope, we'll start cleaning up those things. So if the reference count goes to 0, then Ray knows no one's using that, and it'll start to clean it up, with some small exceptions, which I'm actually going to talk about. Yeah. Okay. All right. So we have an object store we can put and get. We have functions called Ray tasks that we can execute, and then we'll just move on to Ray actors. And very simply, Ray actors are just Python classes with that same Ray remote decoration. So super simple. So keeping with our doubler theme, I have this class doubler. It has an initialization that just prints something. And then I basically copied that double function inside this class, except I added another print in here. I really should be using logging, but this is a Jupyter notebook, no big deal. So only gotcha here is you need to use remote on the actor to instantiate the class. So right here, and then you get back a handler to the class, and then so we'll print out the value of that handler, and then to call a method inside the class, it has this pattern where you have the actor handle, then the method, and then .remote again, like this method is a task, right? So that could throw you a little bit. I knew it threw me a little bit when I started using classes. But as long as you understand this pattern, you should be good. So we're going to print out the doubler handle here. And then here at the bottom line, we set the value of 10. And then we're going to just say 10 doubled is. And then we're going to execute this method and do array get on it. So shouldn't be any shock that 10 doubled is 20. And the value of the doubler handler is an actor that has a class doubler, and then that's, I'm assuming, a memory address of that location.
I noticed it did not print out your print initialization thing.
Ah, yes. I'm gonna.
Okay.
Yep. That's
Sorry,
great.
yeah.
That's great. Yeah, I'll show you that here in a second. Named actor. So you have this actor, you can put methods in it, they execute kind of like Ray tasks. Now you're just learning a new way to organize your Ray code. Actors can have state, but again, you probably, if you had something like write to a database, you need to reopen that connection because you don't know what Python process is going to execute that, so you got to be careful. So you can name actors. So I have a new one here called greeter that its initialization takes in a name, stores it as an attribute, and then when we ask it to say hello, it just says hi, name. And so here's something new, other than me coughing. So we're going to introduce this options in between the actor and the .remote function here. And so this is where we're going to introduce the name of greeter, and we're going to get this greeter if it exists. Sorry, if it exists by name, we're just going to get that one. So basically, we're creating a greeter here with the name Bob, and then when we ask it to say hello, we should expect it to say hi, Bob, right? Hi, Bob. Okay, now we'll try a greeter with the same name, get if it exists, with a new name, Sue. So we're going to name this the Sue greeter handler. We're going to do the same thing. We're just going to ask it to say hello, returns an object reference, and we're going to get it. Hi, Bob. So what's happening here is if this by name, this greeter exists by name in the object store, greeter, and when we tell it to get if it already exists, so it basically ignores this value of Sue. Okay, so there's ways you can control this here. And so if I really needed a Sue greeter, I'd have to use a new name. That would work.
Is the name option, is that just coincidental that you named your parameter name?
Yes,
okay.
yes. Yeah.
Okay.
In the Python or in the array docs, they call it value, and I didn't want to call it value, but now I see maybe there's a reason. So you can retrieve an actor handle by name. So rather than creating it this way, I can just say array get actor by name greeter. And so I'm going to set it to a new handle variable and do the same say hello stuff. And it says hi Bob, unsurprisingly. And if we print out the greeter handle for all three of these cases, we can see they're identical. It is the same greeter because of this, the naming and get if exists. So I don't use naming a lot in this particular case, but as we talked about for the object store, if this greeter goes out of scope, this greeter will get cleaned up, and so it only has a lifetime while something is pointing at it. And so that brings us down to actor lifetimes. And so here I have this very base, actually empty class I'm calling singleton that does nothing. Okay, I'm creating the singleton with that options thing. I name it a singleton, but this time I'm giving a lifetime called detached, and then I execute the initialization here. Notice I'm not even I don't even keep track of the handle here. I don't keep track of it because it doesn't care if you have any references to a detached actor at all. It will keep it around, and you're responsible for cleaning it up. Yes.
Can you zoom in?
Oh, can I zoom in more? Yes. Thanks for bringing that up. Does that work?
Just a bit more.
That is a little better. How does it look one more up? Yeah.
One more.
Oh yeah. That's
You like that? Okay. Thanks in the back. Okay. So notice I'm not capturing the handle here at all. But like we did before, I can get the actor by name and print out the handle. Then I can do a whole bunch of things with a singleton, and it can go out of scope. It doesn't matter, but I have to kill the actor when I'm done with it. And that happens through array kill with the handle, basically. So let's execute that cell. And we can see the actor singleton, that was its memory address. I killed it. So if I try to get that actor again, it's going to throw an exception. Value error, actor not found, blah, 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 big array problem. So I use the detached actor for stuff like configuration, right? You just need one guy to tell you like where your servers are or whatever. So that's something interesting. Okay, so now we'll move on to like a somewhat trivial example, and then we'll get into some kind of fun stuff. So we'll import this actor pool. I'm going to use my favorite faker to create a list of 10 integers up to a maximum value of 50. And so I will store that in the needs doubling variable. And then I'm going to create an actor pool, and I'm going to make 2 new doublers and put them in the pool. And then basically I'm going to execute the double method inside the doubler actors on each value in that list. And so I'll print out the list itself, the needs doubling, and then I'll print out basically the results. Okay, so 33, 66, so on and so forth throughout the whole list. Now, you mentioned not printing out the initialization or the values. If we go back to the dashboard, and we've only been really looking at this cluster, we can look at actors, and we can see, like, first off, remember that singleton that I killed? It's dead. It's in here dead. And then we were messing around with a doubler and a greeter before, but these two are the ones that were in my actor pool, and I guess you might want to see this. So if we go to the logs for these and look at the standard out log, you can see here that's where the initialization happened, and then this particular one processed the values 33, 44, 650, and 48. And if we look here, what was it, 33, 44, 650, 48. So it looks like it processed every other one. And then if we go back to the other doubler and look at its logs, it did initialization 47, 32, 27. I'm not going to remember them all. So 47, 32, 27, it basically processed every other one. So that's how that worked. So that should answer your question. All right, so now I'm going to basically shut down the cluster, because now I want to get into some other things, but this is a good place to pause and ask if there are any questions so far.
In the pool example, are there that seemed like a kind of a round robin strategy?
Yeah.
Just 2 of them. Are
Yeah.
there different strategies that can be applied, or how does it figure out how to distribute the work?
Yeah, so it gets complex. I can tell you that the Ray people tried to deprecate the actor pool, and there was a big hubbub about it, and so they kept it around. They definitely prefer you using Ray data, because that's way more elegant, especially when you start talking about auto scaling and stuff like that. As far as the strategy goes, I'm not sure.
Okay.
But active pools should be used really specifically or for these kinds of examples. Okay, anything else? No, okay. Hopefully this is cool.
It is, yeah.
All right, so this is straight from the Ray docs. We're going to estimate the value of pi. If you want to impress everyone, you can say you did a Monte Carlo simulation. But all this really means is we're going to use a unit square and put a unit circle inside, and then we're just going to splatter it with a bunch of dots. And we're going to compare the values, the number of dots inside the circle with the total number of circles, and we're going to multiply that by 4, and that's going to be our estimation for pi. Now, as you might imagine, the more dots you can throw at this, the closer your approximation is going to be. So this is a good use case for Ray. So let's walk through this code a little bit. I'm trying to use this just as a standalone script here, so we're going to re-import Ray and a couple other things. Because I've run through this Jupyter Notebook a couple times, I've made the mistake of trying to reinit it while it's already running. So I have this safety thing in here that if Ray's running, shut it down, then restart it. I want to start it back up with 8 CPUs this time, not 4. And we're going to use an actor and a task in here. The actor is just going to keep track of progress, and so it's going to have some kind of state, which is a good thing for an actor to do, or good use of an actor. And so it's just going to know the total number of samples that we're going to attempt here, and then it's going to keep track of each worker's progress so far, and it's going to happen through this report progress method. And then we can query every once in a while how far are we along for each each task, we're going to add them all up and compare it to the total number of samples. When this hits 1, we know we're done. So that's the actor. The sampling task, that's really just randomly picking a point inside that unit square, and then we're going to check if it's inside the circle, and we're just going to accumulate the number of points inside the circle. We're going to call the progress actor. It gets passed in as an argument into task. Every million dots, we're going to report back to this progress actor. And when we're done, when this task is done processing its samples, then it will just report the final progress and return the number of points it has inside the circle. Okay, so hopefully that's okay with everyone. So here's our setup. I'll create a array cluster with 8 workers. So we're going to have 8 sampling tasks, and we're going to use 100 million points per sampling task. So we know our total samples is 800 million. So we're going to create or instantiate our actor using .remote and with an initialization parameter. And then we're going to call the sampling task 8 times basically. And the results will be like a list of object references, right? So then we'll go through the array progress, and we're just going to loop here forever until the progress is 1, and then we break out of the loop. Then we'll get the number of points for each task that is inside the circle, multiply that by 4, divide by the total number of samples, and then we'll have an estimation of pi. Make sense?
Yeah, cool.
Okay, so really we're just shotgunning inside of a circle. And so we'll run this, and actually I want to bring up the dashboard again, because this is going to make my fans whir in my laptop, and this is a good chance to kind of show you, here it goes, a good chance to show you what's going on with the cluster. Okay, so Ray is kind of booting up here. The dashboard, I find lags a little behind like what's actually happening. So sometimes I'll force a refresh. You can see my desktop is at 51%. If we go back here, we can see, remember, every 5 seconds we're asking the progress actor, how far along are we? If we go back to the dashboard, okay, so now we can see all 8 of our tasks are jamming on each of their respective cores at 100%, which has got my fans going and my CPU usage at 50%. And so we'll just let this churn. Now what's surprising, like, don't get your hopes up about the accuracy of this simulation, because I want it for 800 million points. I would think that it would be like really like MIT kind of levels of precision, but it's not. It hasn't been, right? So here's our estimation of pi is 3.1417 versus 3.14159. But you'd think 800 million points, you should be closer. But anyway, this is just showing how we could be smart about running on 8 simultaneous processes. Okay, it's still a cool example, I think.
So not a good method for calculating all the digits of pi.
Yeah, but you can say you did a Monte Carlo simulation. So you can try that out a little bit. I experimented with this and actually went much higher with these numbers, but I quickly discovered that I was bored and you would probably be bored, and I didn't want to sit up here talking that long, so we'll just keep it at 800 million. Okay, and the last example that I wanted to show, and this is going to get to one of the questions about dependencies, and it's related to a web scraping talk we had last year. So that's what this is, and here's the link to the Ray docs that talk about that. So I'm gonna pip install Beautiful Soup because that's what this web scraping code needs. And so this is not a Ray implementation yet, and I'll just walk through this really quick. So we're actually going to web scrape the array docs themselves. So we're going to start at the docs at the latest version at index.html. Down here in this second cell, we're just going to call this find links with this base, and with this index.html. And so in find links, we're going to just call it with a default depth of 2 because we're not really interested in scraping their website. This is just an example. Requests will pull the website, and Beautiful Soup is going to basically look for all the href. So if we go to docs.ray.io and we do view page source, and we're going to need to zoom this a lot probably and look for A's. Let's go down to a couple here. Okay, so like here's an A tag with an href of excuse me, getting started, use cases, examples, installation. So really that's what this is looking for. This code is looking for that. And then, well, it's going to find all those elements. This extract links here actually gets the link. And then we're going to call the find links recursively, decrementing the depth until the depth is 0. And then we're just going to return the links here. All right, so let's define these functions, and then I'm going to time this, and then I'm going to print out the number of links we followed, and then just because I'm going to print out the first 10 of those links. So this will take a second. No, there's no sense going to the dashboard because this is just Python code.
Yeah, you're going to be I/O bound anyway, not CPU bound.
Yeah, exactly. I think it was 30 seconds or something when I did it last, so it doesn't take that long. So we return a set of links that is 289 length, and then the first 10 were like train, compiled execution graph, so on and so forth, right? And so, yeah, it took about 33 seconds. So now I'm going to do something that will expose like dependency management to you. As I'm going to uninstall Beautiful Soup on my host, and then I'm going to I think I have array running, right? So I want to shut it down and I want to restart it with 6 GPUs. Because what I want to do is use that same base URL, but I want to go through the index.html like we just did, and then look at ray core, ray data, ray train, ray tune, and ray serve all in parallel at the same time, right? And so I'll just execute this now so we can get this ray shut down and startup going. But this is kind of the last thing I wanted to show you is in this task. Remember, it's a Python function wrapped by Ray Remote, but I'm telling it for this task, reserve 1 CPU, and I'm going to give it a runtime environment that installs Beautiful Soup in the task runner. So it's not in my virtual environment. I can make the task runner install it as a dependency. So since our script here requires Beautiful Soup, we're just writing this task that wraps that function, and it requires Beautiful Soup. So there's a lot you can do with Ray to kind of get wild. So now if I execute this, we're going to have six processes. Yep, there's our 6, and then we're just waiting for the CPU delay here. And each of my CPUs are going to do that same depth of 2 at each of these endpoints. Now you can imagine this could be 6 different news organizations, right? It doesn't have to be 6 endpoints of Ray. So you could distribute your web scraping using Ray. So it doesn't have to be a machine learning workflow. And so here I print the length of the list that we return, and I just print the first three because it gets a little crazy. So 289, 169 links, 83, so on and so forth. It took about the same amount of time, but we went through so much more, right?
Can you comment a little bit more on the num CPUs equal 1? That's what I...
Num CPUs is 1, yeah.
You fan that out to, I think you said 6 CPUs, but
Yep.
I'm having a disconnect on what's happening there.
Oh, so this is like a resource reservation. So whenever this task run, so I could like change this to 12, and then say internally I need 2 CPUs for this task because I'm doing something wild with it, or you can go fractional, which you can also go fractional with GPUs too. So my 3060 here, I don't know if it has 6 or 8 gigs of RAM, but if I have a small model, I could actually be serving two models, and I could make fractional reservations for this particular task. It gets a little tricky, but I just wanted to expose it to you. All right, so that's basically the end. Hopefully I answered all your questions. I have a link at the end of the Jupyter Notebook about design patterns and anti-patterns. I spent a lot of time in here when I was writing Ray code because like stuff like this, calling Ray get inside of a loop hurts parallelism, right? So really you should just get a list of refs and call Ray get once, right? And so when I am mentioning these things in the Jupyter Notebook is because I learned a lesson the hard way. So so that's basically it. I'm going to call Ray shutdown, and that's the end of the talk. If you have any questions, I'm happy to answer them.
Thanks, Dean. I'm curious on like some of the real world use cases you have.
Yeah.
How have you found this? Because it's one thing to like I get adding numbers and seeing pi and that sort of stuff is cool, but how have you found? What has this done for your organizations aside from give that very early example of took something that took 6 weeks down to 5 days?
Yeah, so that's one. So with my company, we have a lot of videos, and so let's just say I need to transcode 1,000 videos from FLV to MP4, right? A lot of computer vision workflows can benefit from using Ray. So instead of pulling them down to my laptop, for example, and running FFmpeg and then uploading them, right, I can spool up a Ray cluster, and if I had a big enough budget, right, I could spool up a 1,000 node Ray cluster, have each one of the nodes pull one video down, transcode it, and I'd be done in an hour, or whatever the length is to transcode the longest video, right?
Okay. Do you have any comparison? Have you heard of Dask?
Yeah.
Dask seems, I know very little about it, but one thing it seems to do is seems to be transparent about the way you were interacting with Ray.
Yeah.
There were Ray-isms, I'll say. Like
Ray-isms, yep.
Interacting with this object store and certain references and stuff.
Oops.
Nope. Dask, by comparison, from what I know, is more like you have your Python code and we'll figure out how to distribute amongst our cluster. Maybe that's naive on my part.
Yeah.
Do you know any comparison between Ray and Dask and strengths?
So the Ray ecosystem is huge. You can actually run Dask on Ray. So as far as I know, I think Dask is NumPy parallelization or running NumPy distributed. So if you need to run some NumPy execution, you can use multiple nodes similar to Ray, but I think it's only for NumPy. So so Ray has a lot of integration with some of these other tools that you're talking about, scikit-learn, Dask, Modin, a bunch of other things. If you are in this world, will make a lot of sense.
So it tries to be a lot more general purpose.
Yeah,
Okay.
Yeah, for sure. If I didn't mention before too, like if we go to ray.io, basically we're in good company. There are a bunch of, Uber, OpenAI, Spotify, Instacart, they're all big users of Ray. So it has a lot of backing. Anything else I can help you with? Who's interested in using Ray in their workflow?
Actually, I think that will work well for NiFi.
Yeah. Perhaps. It's not Ray related, but what's the bang Python syntax? I've never seen that before.
Oh, that's a Jupyter Notebook thing. Like you're talking about this, like
Yeah.
this, yeah.
It's
So
like
that's just
command.
run a command instead of
outside the
yeah, like in a shell rather than a Python
Okay.
Python code. Yeah, so it's a Jupyter Notebook ism, just like this % time just will give me the time it takes to execute that cell. Yeah.
Any other questions?
Are there use cases with Ray using like for training the LLMs in terms of like I have a personal project like working
Yep.
on like a RAG, like a retrieval augmented kind
Yep.
of
Yep.
system using local LLMs.
Yep.
So I was wondering like Ray, if I have like a bunch of documents, like how would Ray fit into that training?
Yeah, so Ray has a big LLM offering, and Ray has this Ray Train, which I covered in the beginning. Maybe you're walking in when I talked about that. But you can do distributed training on Ray, and Ray also has Tune. So if you need to do hyperparameter tuning, it can do that. There's specifically in here some LLM stuff, and I've been talking with the Anyscale folks for our managed solution, and they're really big, heavy on LLM offerings.
So is this
Yep.
like Ray? I know it's like open source, but
Yep.
you know I can kind of do my own training using Python scripts and PyTorch. But is Ray like, is this like an industry standard kind of thing, or is it useful for like scaling easily? I know it's useful for scaling, but
Yeah.
is this like an industry standard library that's being used? Or?
So the pip Ray package, pip install Ray, that's open source. Anyscale has their own version of Ray with a lot of internal optimizations, and so that's kind of part of what they offer in their managed platform and their optimization library. But Ray itself is open source, so that's how I've been leveraging it for a long time until just recently. Yeah.
Any other questions? All right.
Cool.
Thank you, Dean.
Thanks for having me.